Next, we'll talk about OWL entailments. Necessary conditions, which were covered above, are when we have the class is a subclass of the property restrictions. So, for example, child of parent has at least one value of type person. Necessary and sufficient conditions, which were also covered above, we have the class is equivalent to the property restrictions. Example, a person is a parent if and only if child has at least one value. These are some of the constructs in OWL that will have entailments or implications, things that can be inferred. Consider domain and range implications. If the RDFS domain of P is C1 and we have a triple in our knowledge base P of instance 1y, then that infers that I1 belongs to the C1 class. In other words, if we know the domain of a property and we have a triple with that property, then the subject of that triple should belong to the domain class. Likewise with range, if the RDFS range of P is C2 and we have a triple P of I1 is Y, then that implies that Y belongs to the class C2. In other words, if this triple exists and the range of P is C2, then Y can be inferred to belong to P2. Now, this domain and range entailment is sometimes a little surprising to people who are thinking in terms of constraint languages. In a constraint language, you would expect the domain of P C1 and a triple where P of I1 is Y. You would expect that to mean that if C1, if I2 is not a member of the C1 class, then it's a type error for I1. Likewise for range, if we have this triple that P of I1 is Y and the range of P is C2, then if Y doesn't belong to the C2 class, then we expect a type error. And Saddle does do type checking, and the results are displayed either as errors or warnings, depending on a preference setting. You can choose whether type checks or errors or just warnings. The actual OWL entailments that are inferred from all of these various conditions depends upon the reasoner and the reasoner settings that are chosen. Just a word of warning, I guess, or an observation. If you turn on all of the implications of OWL entailments, then OWL reasoning can be computationally very intensive. One of the last subjects that we want to talk about is rules. So if-then rules implement the propositional logic implication operator, the arrow to the right. It's of the form when conditions if are met, then conclusions then are inferred. So let's look at an example using our genealogy model concepts. We could write a rule called parent from birth. Remember, we had this birth class construct, and we want to be able to infer from that the existence of parents. So we can write a rule that says if B is a birth and B has baby BB and B, the birth, has mother M, then BB has parent M. So if you have a birth and it has a mother and it has a baby, then that baby has a parent who is the mother. This is one way of writing rules in the controlled English of Saddle. There is another way of writing rules where instead of explicitly using variables, we use indefinite and definite articles just as we do in natural language English. And you have to set the preference for the use or not the use of indefinite and definite articles in your preference settings. So in other words, the Saddle needs to know which kind of rule you're using. But if you turn on indefinite and definite articles in translation, then the indefinite article identifies a free variable to be bound, and the definite article is a reference to that free variable. And you can then use ordinals to indicate additional variables. So for example, if you have a person, you might say a second person, or you can say another person, a third person, a fourth person, etc. So rewriting this rule using indefinite and definite articles, we have this rule: if a parent, so that creates an X, has baby, a person, so that creates a Y, if you will, a second variable, and the birth, that's a reference back to this birth, so that's referencing the first free variable, has mother, a woman, here's a third variable, a free variable, then the person, that was our second variable, has parent, the woman, that's our third variable. These rules are subtly different because here we said B is a birth, and after that we just said B has baby BB, but we didn't say that BB is of any particular type. Here we said BB, that is the value of baby, we said it's a person, so we've provided a little more information or constraint in the rule. We've said that BB has to be a person. Often that's what you intended anyway, but this rule is a little more restrictive. Rules are not a part of the OWL standard. However, you can see that since they implement the implication of propositional logic, they are certainly compatible with, and they're often used with OWL and processed by OWL reasoners. So some of the rule implementations include the Semantic Web Rule Language, SWRL, Jena rules, which is what is used by the Jena reasoner in Saddle, and Prolog, which is the rule format used by the Prolog reasoner in Saddle. Whatever reasoning is used, reasoning must seamlessly integrate OWL entailments if it's an actual OWL reasoner and rule inferences, because an OWL entailment may cause the conditions of a rule to be satisfied, or the conclusions of a rule may cause the conclusions or inferences of a rule may cause the conditions of an OWL entailment to be satisfied. So reasoning must be integrated together in order to get all of the expected results. Note that OWL entailments can be selectively implemented as rules, possibly improving performance, so that we don't have to turn on all of OWL reasoning with its computational intensiveness. We can turn on only that part of OWL reasoning that we need if we're using rules to do the OWL reasoning. Saddle currently offers two reasoner choices with compatible translators to translate from the controlled English representation into OWL and the appropriate queries, rules, etc. The Jena reasoner is an RDF rule engine with its own rule syntax. The OWL entailments are by rules, and there are various possible rule sets that are identified by the Jena model specification. A link here from the slides that can be set in the project properties. The SWI Prolog reasoner uses SWI Prolog, which is a freely available Prolog reasoner that's compatible with RDF and triples. It uses the SWI Prolog as a service to do OWL reasoning, and OWL entailments can be accomplished by rules, but you have to supply those rules. There aren't any provided rules with SWI Prolog. Note that other reasoners can be added to the Saddle environment by wrapping them in the appropriate interface classes and providing a translator also wrapped in the appropriate interface classes, so that the translator will translate the constructs into the appropriate representations, and the reasoner will then reason and query using that reasoner and associated query engine. In the past, for example, Saddle has supported the pellet reasoner, but that is no longer really open source and is no longer supported by Saddle. Finally, let's talk about built-in functions in rules. You may recall that in predicate logic we have defined the function symbol as a symbol that takes 0 or more arguments and returns another non-logical symbol. Rules use functions, they're also known as built-ins, to compute non-logical values. These functions or built-ins are used for math operations like addition, subtraction, multiplication, and so on, for string operations, for list operations. For example, suppose we had the rule to compute the area of a rectangle. It might say if x is a rectangle, then the area of x is the height of x times the width of x. So from our triple, from our knowledge base, we could find the rectangles, we could find the area of the rectangle, we could find the height of the rectangle and the width of the rectangle, but there's no way in our knowledge graph that we can multiply that value of height and that value of width together. So what happens is in the translation, this translates to a built-in. In the Jena rule translation, the rule is given here, and the relevant part is this product of V0, V1, V2. So what happens is product takes as inputs V0, which came from the height of our rectangle x, V1, which is the width of our rectangle x, and the product of those two is bound to the variable V2. Then in the conclusion of the rule we can say that our rectangle x has area V2. Note that users can define and add their own functions to do whatever procedural programming they need to do to compute non-logical values. And this can be done in Jena, or it can be done in SWI Prolog and many other rule reasoning representations, and also in some query languages. And there are links from the slides to documentation on how to do that. So that brings us to an exercise using the genealogy model previously constructed with the instance data. In the genealogy model, that is the meta model, add a rule to the model which will infer the sibling relationship. Then add a query, and you'll probably want to add this query to your instance data so that you have the so that it will have access to all of the instance data. Add a query to find all sibling relationships. Now you're ready to exercise the query. Select the saddle perspective. That would be from window perspective, other perspectives, other saddle. When you get to the saddle perspective, then you can run inference. So you can, from the saddle drop-down menu, you can select test model. You may or may not get any results from your query. If not, you may need to add some instance data in order to obtain results. In other words, you may not have any instances that actually match your query or the rules in order to infer the sibling relationship. Once you've completed that, then set the Jena reasoner's model specification to ALMEM RDFS. The default will probably have been ALMEM if you haven't modified it. Set the model specification to ALMEM RDFS. Do that by going to Project Properties, Saddle, then Reasoner Preferences. That will make Jena visible. Click on Jena, not the checkbox in front of Jena, which selects it as a reasoner. It should already be selected, but click on Jena itself, which will select that reasoner. Then click on the Edit button, and then you'll get the actual preference settings for the Jena reasoner, and you can set the model specification to ALMEM RDFS. Now rerun inference and compare the results to the results you got before you change the model spec. Optionally, go back and set the Jena reasoner's model specification to ALDLMEM rule. That tells the Jena reasoner that you want to do all of the description logic entailments that are implied, that are supported by the GenRule engine, implemented as rules, and rerun inference. The first step in this exercise is to create a rule in the domain model in genealogy to infer siblings, or to infer siblings. So we'll call this the sibling rule. And you can put a colon, you don't have to. You can put it on different lines, but you don't have to. If X has parent Y, and Z has parent Y, and we need to, so in other words, X and Z have the same parent, but we can't let X equal to Z, because otherwise we would infer that people are siblings of themselves, which doesn't make a lot of sense. Then X has sibling Y. So that's one way to write the rule. We could also write the rule using indefinite and definite articles. And so if we do it that way, we'd have sibling rule alternate, if you will. And here we would say, if a person that creates an implicit variable has parent a second person, and a third person, has parent the second person, then the person, that would be the first person, has sibling the third person. Okay, so we have a bunch of errors here. It says the use of articles is not enabled in preferences, but the content is only valid when enabled. So here we would go to our preferences, and we'll go to saddle. We have project specific settings enabled. Go down to translation settings, use definite and indefinite articles in validation and translation. If we do that, and then we save, well, maybe we'll have to clean the project. The use of articles is not enabled in preferences. I thought I just enabled it. Let's take another look here. Well, those are, interestingly, sticky markers. Not entirely expected, but occasionally the development environment has some sticky markers. So those error markers from previously were there, and they didn't get cleared. So just for kicks, let's go into genealogy and let's look at the rules. So we'll open these in a text editor, and let me combine these windows so we can see. So you'll see that the difference between these rules is that in the case of the implicit variables using indefinite and definite articles, we have a type person, whereas in the rule without, there is nothing that specifically says that these have to be instances of person. Other than that, those are or the same rule. So that's a difference that is typically not overly important because you probably want to infer those memberships anyway. So there we have it. Okay, so the second part of the issue of the problem, and actually let me cancel out, or let me comment out this rule for the moment. And going over to the Adams family, let me get split screen here again. Find all sibling relationships. Let's see, we don't have a sibling relationship query, do we? Oh yeah, no we don't. Okay, so let's comment out these queries for the moment, and let's just work with a sibling query. So ask, and it's a simple query, so we can just say select S1, S2, where S1 has sibling S2. Ask has to be camel case. There we go. Okay. So if we run this query, let's see what kind of siblings we get. We didn't get any siblings at all. That's very interesting. Let's look at our data in light of this rule. So we need to have something which is known to have the same parents. So one thing we can do here to try to debug this is we can ask for an explain, and let's do a ruling sibling rule. This is a useful thing to try to understand why a rule isn't firing. So we'll test the model again. And now let's look at what we get. So, explanation of rule, sibling rule. So, the first premise is X parent Y. And this had 3 matches. John Quincy Adams is a parent of John Adams. I'm sorry, John Quincy Adams has parent John Adams. John Quincy Adams has parent Abigail Adams. And John Adams has parent John Adams Sr. So you might be starting to see the problem. So the second part of the rule is that we're adding that Z has parent Y. So now we're going to have 2 children have the same parent. So John Quincy Adams has John Adams. So we haven't yet gotten to the part of the rule that says X can't equal to Z. So what we have is John Quincy Adams has parent John Adams, and John Quincy Adams also has parent John Adams, likewise for Abigail Adams, and likewise for John Adams having parent John Adams Sr. So you can see that the only rules that match, the only instances that match are redundant, and as soon as we get to the next one, which is X is not equal to Z, we have no matches. So we don't have any data actually in our knowledge base that will satisfy this rule. So one thing we could do, just for kicks, let's put in a sister of John Quincy Adams. So what we're going to do here is we're going to put in Amelia Adams, and she was also known as Abigail Nabby Amelia Adams. And she married a Smith, so sometimes Smith was thrown in. And she's actually a woman. And she has the same parents, but she doesn't have the same birthday. She was born on the 14th of July, 1765, so she's the older sister of John Quincy Adams. So we'll save that. We'll clear our console window just to avoid any confusion. We probably don't need this explanation of the rule anymore. And we will rerun inference and see what we get. Okay, now we get that Amelia Adams has sibling John Adams. That's not correct. So what is going on here? Okay, I wrote my rule wrong. This should actually be has sibling Z, not sibling Y. So we'll save that. Change and try this one more time. Okay, now we get Abigail Amelia Adams has sibling John Quincy Adams, and John Quincy Adams has sibling Abigail Amelia Adams. So let's play around with one more permutation. Let's change rules here and go to this rule. Let's just make sure I didn't mess it up the same way I messed up the other one. So we have a person has a parent, a second person, a third person has parent, the second person, then the person has sibling, the third person. So that should be correct. Okay, so we'll try running our model once more, and we don't get any results. So if we look at explanations again, I don't have a sibling rule, so I want to actually explain the sibling rule alt, and we'll run inference and see what we get. So the premises through had one match, which is John Adams, and through 2 had one match, which was John Adams. So when we get to 3, we have no matches. So the problem is that we are constrained to person here. And remember, we have the type constraint that the variables have to be persons. And if we look in our data carefully, once again, John Adams is the only individual here who is declared to be of type person, belong to the person class. So that's why we don't get any results. But if we look at this rule, there's no such constraints in it that there has to be that the bindings of the variables need to be of type person. So therefore, we pick up the parents of we pick up John Adams and Abigail Adams as parents, and we see their 2 children are siblings. So that explains that. Now we're going to go into our preferences and change the model spec. So let's go to Project Properties, and we'll expand Saddle. We'll go to Reasoner Preferences. It's the Jena Reasoner in question. And our Jena ontology model spec is ALMEM. We want to make it ALMEM RDFS. We'll save that. Apply and close. It should have automatically cleaned the project. Let's hope that it did. And now let's go ahead and uncomment all of our queries and get rid of the comment out the explanation. And now let's just run the queries and see what we get. So starting with the first query, where we're looking for spouses, the results of this query are not any different for the spouses. If we look next at the query for people and optionally their gender, date of birth, baby, so on and so forth, you'll see that we have a significantly expanded set of options here. Before we had John Adams, male. This first line was the only one we had. Now we have Abigail. There's some things we don't know about Abigail. And that's because even though we said she's a woman, we don't have any level of vowel reasoning turned on that would infer gender from that. Likewise, William Smith. There's lots of things we don't know about him, but we have inferred that he's a person, whereas where is William Smith? William Smith. I must be blind. There's William Smith. All we know is a man, so we don't know much about him, but we inferred from the fact that he's a man that he's also a person, as we did for Abigail, and so on and so forth. So what's happening here is we turned on transitive reasoning, so it infers that instances of subclasses are instances of the class, and so we get a lot more results than we did before, matching our query. And last time, when we ask about parents, we just got John Adams had parents, John Adams Sr. and Abigail. I'm sorry, that John Adams had parent Susanna Boylston. And if we look down this list, we have a larger set here. We have John Adams. We have the two that we had initially, but we have additional ones. That's because, again, we've inferred more members of the person class, and our query started out by narrowing things down to those things of type person. So that gives us some additional ones, and as for siblings, there's no change because we're using the rule that doesn't have the person. We are using the rule as a person in it. I'm sorry. Before we did not get any matches using this rule, but now that we're inferring all of the instances of person by the transitive reasoner, we now get the siblings that we got before using the other rule. So that is the end of that explanation. Okay, so lastly, we're going to set our model spec to one which uses rules to try to do entailments. So we're going to set this to al-dl mem rule. So this is going to include some fairly serious al entailment reasoning. So we will clear that, and then we will ask it to run inference. And you'll observe that it's gone off to think about it for a while, and then it came back. But you'll notice a couple of things. First, it took a lot longer than it did before, and you can turn on timing in preferences in order to get exact timing for how long things take. And you'll notice that we're getting a lot of blank nodes. These are B nodes. We're getting a lot of blank nodes here in our query results. And that's because we turned on lots of al reasoning that maybe we weren't expecting to be turned on. Maybe we have these constraints. These constraints combined with domain and range inferences and so on will come up with generate blank nodes that we'd have to do some significant deep diving in order to be able to explain what each one of them means. So it isn't necessarily desirable to turn on al reasoning unless we really know that we want all of the different kinds of al reasoning. As an alternative, let's go back to our properties And let's set it back to ALMEM-RDFS so that we're doing transitive closure. And now we're going to go in and we're going to add one more rule here. We're going to add a spouse rule to implement spouse symmetry. So instead of having symmetry by regular entailments, we're going to do it very surgically by saying if X has spouse Y, then Y has spouse X. Very simple rule. We're not going to try to apply it to everything in the world that's symmetrical, just to our spouse property. And if we do that, and we rerun, noting that we have gone back to our transitive reasoning only. We run our test model. Now if you look at these results, you'll see that we don't have all of these blank nodes inferred, that we've really just inferred the things that we kind of probably expected to be inferred. And that includes that, let's see, where's our spouse? That includes spouse symmetry. So we have William Smith has spouse Elizabeth Quincy, but Elizabeth Quincy has spouse William Smith, and Abigail John, John Abigail, and so on. So we've inferred the symmetry of the spouse property. And I think that wraps up that exercise. I'll just add a note. I just realized that John Adams' mother is Susanna Boyle Stun with a T. And in this exercise I was confused, maybe the previous one, and left the T out and was writing and saying Susanna Boyle Son. I apologize. There are on the last slide some links for additional information on OWL, on Saddle, and links that allow you to access this tutorial either as video or as slides. I hope that you've enjoyed this tutorial in the foundational concepts of semantic modeling, and I wish you well in your modeling endeavors.